In this playlist, I take you through the analysis for regression of XY data sets. Let me just give you a brief overview of what we're trying to do. So when I say XY data set, what I mean is that the data can be plotted on simple two-dimensional axes, such as this one. We are most likely measuring some value y experimentally and seeing how it depends on some parameter x. So in other words, we're setting some parameter x and measuring y, and then varying x, and then measuring y. And in real life, if you will, data are never perfect. What I'm illustrating here is, let's imagine we expect the relationship to be linear. Let me just draw a straight line. And the line cannot possibly go through all the points. The usual reason why is because there is some error in the measurement, meaning that for this particular value of x, if I repeated measurements, then I would not get exactly the same value of y every time, and that's because there is some sort of random phenomenon affecting my measurement. So I have scatter in my data, and there's nothing we can do about that in most circumstances. So what we actually do is we try to take as many data points as possible, usually at different values of x. We don't always insist that we have repeats at each value of x. And if we have enough data, we can draw a line through the data. And this is often referred to as the best fit line. We're not necessarily interested in straight lines. The data could potentially vary in a nonlinear way. And we could be interested in the best fit curve. So I want to make some comments about what we actually mean by best fit. There are some assumptions here. And one assumption is that your scatter is Gaussian or normally distributed. In other words, if I were to take each data point after I calculate a best fit line, and I were to calculate the difference between this data point and the predicted value, the value that's predicted, the measured y value, and the predicted value from the curve, I'm going to call this E sub I. And I made a histogram of E sub I values. On average, I would expect E sub I equal to 0, and the curve should look like a Gaussian. Let's see if I can draw that a little better. So in other words, a bell curve. The most likely outcome of a certain measurement will be what the line predicts. In other words, E sub I equals 0. But the deviation is generally expected to be Gaussian. And so you could think of this best fit line as being the line that goes through all the peaks, all the highest points of the Gaussian curves defined for each value of x. And the question is, how do you actually calculate it? So the mathematical criterion is normally referred to as the least squares criterion. Which means if I say S sub R is going to be the sum on I, so I equals 1 to n, all of the data points of E sub I squared, I want to then minimize this quantity. So if I can calculate, I also want to point out that S of R is a function of the slope and the intercept in the case of a straight line. I'm going to say A0 and A1. What I mean is that the slope here is A1, the intercept is y equals A0, and calculating the regression or the best fit line can be thought of as calculating the values of A0 and A1 such that the sum squared error for all the data points is equal to 0. The procedure is going to vary depending on the shape of the theoretical relationship. So if you believe your data are linearly related, in other words, y is a linear function of x, then you're going to have to use different procedures than if you believe that it's not a linear relationship. I'm going to talk about 3 possibilities. So the first one is going to be y varies linearly with x. So in other words, y equals A0 plus A1x. Remember, I'm referring to the theoretical curves. Number 2 is I'm going to say y is equal to A0 plus let me change the name here. I'm going to call this, just so that to make it clear that I'm talking about different parameters, I'm going to call this B0 plus B1x plus B2x squared. So this is a polynomial or quadratic relationship. To be clear, remember before we wanted to calculate A0 and A1 such that we minimize the square residual for the data. In this case, we're doing the same thing. We want to calculate B0, B1, and B2 such that we minimize the sum squared residual. Except now we're making a different assumption about the relationship. The relationship is quadratic. And then finally, I'm going to use an example of a nonlinear equation. So y equals C0 times the exponential of x over C1. And so this is nonlinear. There is a little bit of a twist here, and I'll explain this in a later video, but you might think that the polynomial equation is nonlinear, and so you might think that this fitting to a straight line is linear regression, and that these 2 fits would be considered nonlinear regression. However, that actually turns out not to be true. For reasons I'm going to explain a little bit later, polynomial regression actually is linear regression. Even though x and y are assumed to be related in a nonlinear way, it turns out that SR, the sum squared residual, is still linear in the parameters B0, B1, and B2. So the term linear regression actually refers to the relationship between SR and the parameters, but I'll get into those details a bit later.